So, welcome back. We are very happy to have Nikolay Ebel, who's telling us about tensor network renormalization group maps and their fixed points. And please, stage is yours.
Yeah. Hi, everyone. Thanks, Chen, in particular, for inviting me to give this talk. I want to talk today about work we are doing with Slava Ryzhkov and Tom Kennedy. We are trying to study the renormalization group using tensor networks, as title suggests. Let me give you a plan what we are going to do today. First, I would like to introduce you the basic concepts of tensor networks, explain what it is, and what is most important, to explain how to read pictures I'm going to draw. Then I will show how you can take your favorite lattice model and translate it into tensor network language. I will use nearest neighbors Ising example, but I should emphasize that you can take any lattice model with finite range and rewrite it in this language. Then I would like to discuss real space RG techniques. First, I would like to talk a bit about more standard approach about block spins, because I think it will help you to appreciate a bit more how well tensor networks works in this regard. And then we will discuss the renormalization group in tensor network formalism. After this, I will present some rigorous results for low temperature and high temperature regimes of Ising model and some other lattice models, in fact. And at the end, I would like to talk about critical fixed point and what we can say about it. Okay, let's start. So we have a tensor, which is just a table of numbers, you can think, with indices in some set I, index set. I will sometimes I will say index set, sometimes I will say index space, but I think it's more or less clear that this is the same. And what is important is to understand how we draw them. We draw them like blobs with legs, and legs here represent indices. And well, the only purpose of tensor is to be contracted with another tensor. And we will represent this like that. We will just glue legs. And what this means is that we take tensors, we sum over the index which is glued, and this is the contraction. And then the tensor network is really any contraction of tensors. We usually will talk about tensor networks with periodic boundary conditions. And typically, when we talk about some lattice models, we think about some rectangular arrangement of tensors of size n times n. Stretching your imagination a little bit, you can imagine that this is n times n lattice, not 2 by 2. Yeah. Let me, yes?
Because indices that you're taking, they also take continuous values or they
indicate? Yeah. We will assume that I is countable. And in numerics, indeed, we assume that I is fine. Okay. Let's try. Oh, sorry, I forgot to time myself. Yeah, now it's better. Let's take nearest neighbor sizing model. Here it is, very simple partition function, just sum over all the configurations of sigma. And let's first color it in checkerboard pattern. And now let's take one of these yellow plaquettes and define the following tensor. Indices of this tensor are just spins, and its values are these parts of Boltzmann weights, which encode all the interactions we have around one plaquette. Okay, then what one can notice is that partition function itself can be rewritten as product of the same Boltzmann weights summed over all the spins, and so it is a tensor network. Quite easy. Maybe if you have a more complicated lattice theory, you will need to work a little bit more, but it is always possible. Okay.
So can you show 1 second more the previous formula, which is just?
Yeah. Maybe it helps to understand this if I also mention that. So you can imagine that here we have a tensor, here we have a tensor, and they always share one spin. And when we sum over this particular spin and this sum, it is just a contraction of tensors.
But now you're
And when you sum over all spins, you sum over all the bonds here, because each corner here is a bond in the network. Yeah, I would like it to be perfectly clear. So if you
so the product on the plaquettes. So on the left, you were summing over all the spins.
yes.
Now on the right hand side, you're taking the product on all the plaquettes, but the sum is only on the spins on the plaquette. Or...
No. It's still you should have some brackets here. It's still a sum over all the spins. So all I did is just I represented this exponential as a product of smaller exponentials. That's all.
Okay. So you're not you didn't exchange the product.
I didn't do anything.
Okay.
It's just very trivial thing. Okay. Now let us talk about real space RG. Imagine that you have some lattice theory and not necessarily Ising model, and we want to focus our attention now on some block of spins, say two times two block. And what we want to do is we want to replace this block of spins by just one spin, so reducing the number of degrees of freedom. And what you usually can do in using block spin is you consider some function t, such that if you sum it over s is our new spin, you always have one, independently on the configuration of the original spins. Now we can introduce such an RG kernel for all the blocks we have, and we can do a bit of equation juggling now. So we can take this partition function z. Yeah, I think I forgot to mention the most important thing, that we want to replace our blocks without changing the partition function indeed. And this condition is what will help us. So once again, we are introducing these RG kernels everywhere, and then we can write one in this complicated form. And now we can put this one inside our partition function. So we have sum over sigmas, then we have sum over s just. So this. Of our old Hamiltonian. Okay, and now we are going to swap order of the sums. Let us now sum over s outside and over sigmas inside. And now what I'm going to do is I'm going to say that this thing is actually a new Hamiltonian. Is the Boltzmann distribution with a new Hamiltonian h prime that depends now only on our new variables. And so we succeeded in rewriting our partition function in this new form. Now it depends only on new block spins. And this part of all of this, it is an RG equation that explains us how we can transfer our original Hamiltonian H to a block spin Hamiltonian.
This new Hamiltonian needs to be nice, right? It's
Yeah.
local.
So this is an equation in a space of all Hamiltonians, and I'm not going to define it right now, but it's possible, it's doable. One can define this equation more or less rigorously. But let us look at it a little bit. It has a few problems. First of all, even starting from nearest neighbor Ising, if you try to do one RG step, you will notice that after one RG step, you have Ising with coupling of all ranges. So it will be infinite, it will be not bounded.
Can you remind me how to see that?
No, I don't think I can remind it right now. I think you just need to play with it and see it. Yeah, I thought about preparing this, but
No problem.
But yeah, there is such a problem. Okay, so analytical work is quite hard. Maybe you can do numerics. Numerics is extremely expensive. Even if straightforward approach promises you to be exponentially hard, even just to compute this sum on the right-hand side, because you need to sum over all the scheme configurations. And what else is quite unpleasant is that this equation itself is not defined, quite often not defined at low temperatures. And what it means exactly is that you cannot define H prime. So you can define a new probability measure, but you cannot really write it in terms of new Hamiltonian.
So just very quickly, so the first thing, that is the easy way to see that even though the interactions are nearest neighbor, there's long-range correlations between the sigma. So when you do that, their path integral, generically their two-point function can be long range. Right? That's why you have this infinite range.
Okay.
So and also this log T, so there was not T in the Ising model, there was just J. So you mean
log
the same?
T is big J.
Yeah. So so you're saying if you do this block spin transformation at big J, the thing is not good.
Yeah, not even for big, just for big J, not even for only Ising. You can define a notion of what is low T in general. It is a situation when you have more than one ground state for your Hamiltonian, and in this situation, quite often you cannot define the new Hamiltonian, so it just doesn't work. There are still some approaches of how to work with this equation. I don't want just to tell you that it's a bad equation, and that's it. So I think the first successful numerical thing which was done by Wilson, he combined this with some perturbation theory and managed to, for example, compute the critical exponents of Ising up to 0.1%. But to my knowledge, until now, no one managed to improve this anyhow. Another method, one can do Monte Carlo arXiv, and the idea is actually very nice. Instead of doing renormalization of Hamiltonian, you can do Monte Carlo simulation and then renormalize the states you obtain, and this is easy. The only problem is that you need to do Monte Carlo simulation of a really huge lattice to get something to do a lot of RG steps, because after each RG step you reduce the size of your lattice by a factor of 2.
And also the choice of arch map is quite arbitrary. You usually use like majority rule or something like that. But you have no reason to prefer one.
Yeah, but I cannot say that we have some preferred RG map in tensor networks. But yeah, maybe I can reformulate it saying that it's hard to find a good T, have some good properties. Also, there is some attempts to speed up computations using the lattice gas variables. It allows to compute H prime a bit faster, but as far as I know, it still doesn't allow you to go beyond one RG step. So yeah, let's look at what tensor networks may offer us. So we want to take a network of size n times n. I denote this as partition function because this is what it is. A means a tensor A, size times n. And we want to do a G step. We want to define new A prime such that we have a smaller network. And 2 here is a scaling factor. And let me just write this formula down because I want to refer to scaling factor later. Okay, if you draw a picture, what you want looks like this. We want to take big network, get smaller network, and actually it's very easy to do. We can do the following. We can define some tensor J, which would act from a pair of I spaces to I square, and it would be an isometry, so that if we contract it like this, we have 1. And so then we can simply contract a block of 2 by 2 block of tensors A with this J, and this will be our new tensor. And this does what we wanted it to do. Here blue line here means another space, and for consistency, I need to color it here as well. Okay, let us meditate on this equation a little bit. First thing to notice is that now after one energy step, we still have only nearest neighbors contractions, not interactions, but nearest neighbors contractions, which is nice. And I should emphasize this works for any lattice model. It is not Ising specific property. You just take any model, rewrite it in tensor networks, and you have these nice steps, which always remain nearest neighbors with only nearest neighbors contractions. It's a bit unpleasant that we see that index space goes up. It increases its size after one step. And this means that if you want to treat this rigorously, we need to use an infinite I. And also we need to assume that our tensors are Hilbert-Schmidt, meaning that this norm is finite. We need this norm to be finite in order to all contractions be well defined. So all the series are absolutely convergent. And in numerics, we need to do some truncations. But we know how to do these truncations very well, so it's not a big problem. What else is great is that all the algorithms that perform TensorRT are polynomial in one dimension. So it's relatively cheap, we can do this. And this can be applied to any phase. There are no problems in low temperature. We have even rigorous results.
What do you mean by the index space goes up? How do I see that from this picture?
Yeah, let's see here. You see, we started from J that acted from pair of I's to I square. And now we did contraction here, and now this new blue legs, they're indexed not by I, but I square.
Yeah, that's necessary to have this normalization. The fact that the J.
Yeah, because you don't want to change your partition function. But yeah. There is one thing that bothers physicists inside me, is that it doesn't look as we really did anything. We just contracted a few tensors. That's it. And well, the truth is that it's not so simple. Let's look at what we expect to see. We expect that if you draw and
Sorry, just another question. Can you remind me why there are just nearest neighbor contractions after this step?
yeah, just look at this picture. Imagine that you took each block of A's
Yes.
and replaced it with this. And what you end up with is this, right? So
Okay.
you don't have any long range contractions here.
How would long range contractions be represented otherwise?
You just never see them. You just don't have them here.
It would be a line between a tensor and a tensor far away, right?
Yeah,
Okay,
yeah, but
okay.
I don't know of any tensor-RG transformations that would do this. So it sounds quite useless. Okay, so what are our expectations? We expect that if we draw this dashed line that represents Ising model in the space of all the tensors, by the way, now this space is very well defined. We expect that if we start from critical temperature, we will flow to some tensor that describes critical physics. We expect that if we start from a little bit above of critical temperature, we will flow to high temperature tensor, and we actually know how it looks like. You can just rewrite Ising in these terms and take the limit. And we expect that if you start from lower temperature, we go to low temperature tensor, which is, again, we know how it looks like. It just looks like a direct sum of two high temperature tensors, each of which represent the two ground states of the Ising in this space, all pluses and all minuses. And what do we get? Well, this is embarrassing. This is what we see in numerics, really, if you just apply this simple RG step. Nothing looks like we expected. You don't converge to one unique high temperature point. Instead, you have some weird line here, and critical tensor doesn't converge at all. So what is the problem here? Well, the problem is that we really didn't do anything. We didn't try to filter some ultraviolet information from the system. And there is a nice toy example which explains it. So let's take our tensor A and let's extend its index space a little bit. So we just add to I, we multiply I with I new, some small index space. So we need to, and now we connect these red lines with some matrices. So this is our new tensor. Let's now try to apply this simple RG step to a block of tensors A. And let's now forget about J, because basically J is just basic transformation. It is not very physical thing. So what we are getting in the end, after RG, we get a new tensor with the same matrices in the corners. But these matrices come from the previous level of our system. They contain some ultraviolet information, and we didn't clear it up. And such tensors like this, if you don't have anything inside, are called corner double line tensors. And in fact, you can even prove that if you start from in some neighborhood of high temperature fixed point, and you do this simple RG, then you will converge to some CDL tensor, which is just a bunch of junk. It's a bunch of ultraviolet information. Okay, so the procedure of filtering this UV information is called disentangling. And we know quite well how to do disentangling in numerics. As for analytical work, I will give a few comments in a few seconds. So,
Is this conclusion only true for 2D?
which one? This?
Yeah.
Yeah. It's 2D. Well, I don't know. Maybe you can prove it in 3D as well. Yeah. So we see now that to have a good RG map, we need to do disentangling. We also indeed need to do coarse graining, which is just contraction of a few tensors to reduce the network size. We also need to fix the gauge, and I didn't mention it, but let me explain it briefly. We have gauge transformations like this. If you take your tensor and you act on its legs with G minus 1, then you may imagine that you have network, you plug it in, all G's cancel each other, and so this doesn't change anything. We need to fix this gauge somehow. But okay, we can do this. It's not a big deal. And once you have all these components, we will see this nice picture you want to see.
This gauge fixing is just changing the basis of the space. Or...
Yeah. There is actually a very nice story behind it, but let us skip it. Okay. Let me understand how much time I have. So I'm talking for, okay, it's fine. Well, let me briefly mention some rigorous results for low and high temperature regimes. So we have right now three stability theorem, or maybe an instability theorem for low temperature for 2D and 3D systems. For high temperature regime, we can construct an energy map, which means we can define disentangling such that we will see a correct flow around high temperature fixed point. We will see that flow converges to high temperature fixed point. We can use it to prove, say, analyticity of free energy close to this point. In low temperature, we have this result for 2D, result that says that everything behaves as you could expect it to behave. In 3D, I'm quite sure that you can use techniques used for high temperature in 3D to get this result in low temperature, but it's quite a tedious task, and I never tried to do this. I would like now to give you some hint of how disentangling can be performed, but I'm a bit worried that I will not have enough time to talk about criticality, and criticality is a bit more interesting and recent. So let me now skip the part about how to do disentangling and talk about criticality. And then if you have time, I will go back there. So, so we have this nice numerical picture. We expect this, but there is still one question that bothers at least 3 people. Exist IC? What it means? It means the question is, can we really define an energy map that would be defined at least in neighborhood of our numerical approximation of critical point, such that it it has a real critical fixed point. And what I'm talking about now is infinite dimensional tensors. So yeah, this question is a bit simpler than you can imagine, because of course it would be nice to track the full RG flow down to AC, but we need to start from something. And this is a good starting point. Let me emphasize once again, we talk about infinite dimensional tensors and we want them to be Hilbert-Schmidt. I'm repeating this because there are some works which propose critical tensors which are supposed to describe Ising CFT, but the problem is that first of all, they are not Hilbert-Schmidt, and second of all, they go together with some RG map, which is defined for these tensors, but it's very unclear if you can define it in any neighborhood of these tensors. So it's kind of, you have only one point and you can track only the flow of this point. It's not very clear what it gives us. Okay, but this question is still very hard. So I'll try to answer even simpler question. How do we find this critical tensor in the numerics? This question already have a standard answer, which is a shooting method. And how it works. So of course it's false. We take the sizing plan. We take two trajectories for which we know for sure that they end up in high and low temperature regime. Then we take trajectory in the middle, we look where it ends up, we reassess our trajectories, we go in the middle, we repeat this procedure until we get somewhere, we get some critical temperature, such that our trajectory is very, very close to real critical trajectory. It will eventually end up somewhere there, but it will approach critical tensor. Let me now investigate some limitations of this method. And to do so, I would like to explain intuition that we have about G flows and its patterns. So suppose we have some RG step R with scaling factor B. This. We expect the following correspondence. We expect that if we have a critical point and we have some small deviation from this critical point, let me call it O, then this should correspond to small deformation of the CFT model, of the underlying CFT model, with some scaling operator. Well, this is just an intuition, not a rigorous statement, but I'm going to exploit this. Then what is R? R should correspond just to scaling transformation, this factor B. And then if we have this one-to-one correspondence, then when we do scaling transformation here, our K transforms as, our K becomes lambda times K, where lambda is given by B to the 2 minus delta O. So we expect the same thing on the left-hand side. Okay. Then let us look at the spectrum of Jacobian of our RG map close to the critical point. So this.
What does it mean that you expect the same on the left-hand side?
Yeah, I mean we have, yes. And here we have K as well.
Yes.
So we expect that if we apply R to this, then we end up with AC plus K prime O and K prime given by this formula.
What is lambda?
This is lambda E to the 2 minus delta.
Ah, sorry.
So yeah, we have correspondence between tensors and scaling operators. Good. I I need more space. Let us now write down. Yeah, okay. Also, you should notice that this correspondence, this formula, can work only for scaling operators which are not total derivatives. Because if a scaling operator is total derivative, we cannot predict anything because we don't have the deformation itself. Let us now then write spectrum. On the left-hand side, I will write spectrum for R. Here I will write Z spectrum. And I will talk only about Z2 given spectrum, assuming that our G transformation preserves spin flip symmetry. Okay. Then on CFT side, we have identity operator with delta zero. And here we have just AC itself with lambda equals B squared, according to the formulas. Then in CFT, we have energy operator epsilon is delta 1. And here we have some tensor, which I will call epsilon as well, with lambda equals B. Then we have some marginals, but I want to ignore marginals for a moment because they will not change the following argument. And we have some irrelevant operators. This data something 2, and we have total derivatives. Data more or equal than 2. And they give us some tensors with unpredictable lambdas. Well, okay, irrelevant operators which are not total derivatives would give tensors with predictable lambdas, but so we have here tensors with lambda less than 1 for irrelevant operators and with lambda unknown for total derivatives.
So can I ask here on the left, when you talk about this argument, presumably you're just computing the eigenvalues of some matrix.
Yeah.
What is that matrix?
It is Jacobian of a G map at point AC.
Right, but in terms of J, it is like a tensor transformation.
No, it is not a matrix. Well, okay, if you talk about this simple transformation without disentangling, which doesn't work and doesn't make a lot of sense, your matrix will look as follows. It will look delta number R acting on some A. It will be A. And plus three another terms.
I should set that.
Yeah. But well, AC doesn't make sense for this simple transformation. So, but in general, it's something complicated because you have this entangling and yeah. Okay. Let us look at these tensors, and let us denote by A the tensor with the largest eigenvalue here. And let us call this eigenvalue lambda irrelevant. And let us pray that this relevant eigenvalue is smaller than 1. Because if it is not smaller than 1, the shooting method would not work. We would need to tune more than one parameter. But it works, so we know that it's smaller than 1. Then we can describe the G trajectory near the critical point. Let us then describe the G trajectory as follows. So we have tensor AN, which is just the nth step of RG, which will be a critical tensor plus delta T e to the n epsilon plus lambda irrelevant to the n a. And delta t here is a parameter of how well we manage to tune our critical temperature. Okay. Then we can estimate how close we can get to the critical temperature, using this formula. Because if we denote by delta n the norm of an minus hc, then this is something like max between delta t e to the n and lambda irrelevant to the n. Okay, we can minimize it. What we will get is that minimal delta is given by delta t 1, 1, 1 logarithm of b lambda irrelevant. And I hope I wrote it right. Yeah. Okay. Let's go back to the slides. So we have this formula. We can look at our numerics, plug some numbers. We looked at the G transformation with scaling factor b equals 2. We computed its largest irrelevant eigenvalue. It appeared to be 0.3, which gives us delta mean, something like delta t to the power 0.4. So we can expect that tuning delta t to 10 to the minus 10, we will approach critical point with accuracy 10 to the minus 4. And this is what we actually see in numerics. It works quite well. But the problem is that, well, it's not a very good method. Even in an ideal situation where we manage to tune delta t to machine zero for our arithmetic float 64 we are using in our numerics, we will only get to 10 to the minus 7. And this is ideal situation, which will not work because it doesn't make sense to tune delta t much more, because our algorithm have some internal errors inside. And what else is not satisfying about this shooting method is that it doesn't give us any clues of how to prove existence of the critical point. We can search for it as long as we can, but we want to prove existence of infinite dimensional critical point. So maybe we can just
Yeah. Why is there this growth after some steps? I didn't understand. Or maybe you didn't.
You mean this or you mean this?
On the right, there is this polynomial growth. Yeah, this exponential.
Yeah, because look at this formula. So we have here AC plus B to the N.
Yeah.
And B in our case is 2. So what happens here is we start from tensor with very tiny delta t.
So you are applying physicality.
And this line we have only this. But at some moment this term becomes significant, and it starts to deviate us from the critical point.
You flow close to the critical point, but then
and then you flow away.
Yeah, it takes you away, right?
Yeah.
So there is some relevant deformation that you couldn't actually tune to see.
Yeah.
Thanks.
This is what we were trying to do. We were trying to tune it to 0, but
Thanks.
Okay. Maybe we can just solve this equation. But why not? Let's just take it, Ra equals A, and let's use standard Newton method. People know how to solve nonlinear equation. For this, we need to define this new function f of A, which looks like this, and let us meditate on it a bit. First thing you should notice is that if AC is a fixed point for R, it is the same as AC is fixed point for F. And you can see it, imagine that A is fixed point for R, then this term is 0, and we have fixed point equation. And the other way around is A is fixed point for F, this is 0, and we again have fixed point equation. Another thing is if you compute Jacobian of A at the critical point, it will be 0. So F should be a contraction. And we can just iterate F to get to the critical tensor. So is it? Can we celebrate, go to the bar? No. No, we cannot, because for dramatic effect, I decided not to talk about marginal operators here. Let us now look at them. So for Ising model, we have two marginal operators. Well, we we have 4 marginal operators, but 2 of them are total derivatives, so we cannot talk about them. We have operator T01 and T00 minus T11. And so these operators with scaling dimension, which transfers to tensors with lambda equals 1. Which means that we cannot invert this operator because we have non-zero kernel.
This is because you broke rotational symmetry.
Yes. If we manage to preserve rotation symmetry, this problem will not appear. But it's complicated, and we didn't know when we worked on this. We didn't know of a method to preserve rotational symmetry.
But also, I mean, T01, it seems that you have reflection symmetry.
The thing is, this tumbling is well, okay. T01 has. Yeah, okay, maybe you can eliminate one of these by imposing reflection symmetry. Yeah, it's true. But still, until you can get rotational symmetry, you will have one of these. And yeah, we need to solve this problem somehow. And there is actually a solution. You can, well, first solution is to find an algorithm that preserves rotational symmetry, and it seems to be possible. But we haven't thought about this at the moment when we worked on this. And also talking about algorithms that would preserve rotational symmetry, you can devise it in 2D, but then if you want to analyze 3D situation, it will be even harder. So maybe we would like to have some more universal solution. And it seems like we have a universal solution. We can just modify our G step. We can define, instead of R, we can define R circle, which is a combination of R and rotation by 90 degrees. So in pictorial language, we have something like this. Let us then look at this correspondence. Now we have, instead of R, we have our circle. Let me write this. Then it doesn't correspond to scaling transformation anymore. Now it corresponds to a scaling transformation with rotation. So let us write this in complex coordinates. It corresponds to something like this. And then our K, it will be transformed not with just scaling factor, but also with some I to the power of spin of O. And we have the same thing on the right-hand side. So what we have now is that the spectrum of Jacobian of R circ should look like something like this. It should have epsilon with eigenvalue lambda. It should have some T01 with eigenvalue -1 because T has spin 2, and T00 minus T11 with -1, and some relevant operators and some total derivatives which we cannot predict. So we now can define this, and we can work with this.
In higher dimensions, this presumably is less of a problem, right? It's hard. Marginal operators are like exactly marginal, are hard to come by. Like now you have like the stress tensor, but this stress
No,
tensor.
this is the stress tensor.
This is the stress tensor.
Yeah, but it's in 3D, this is not marginal either. This is relevant.
Okay, yes. Well,
So
maybe.
So I mean, it's hard to get marginal operators if you don't have additional
But
symmetry.
in 3D, this energy moment, that's the margin.
Oh, sorry, it's dimension 3D.
Yes.
So yeah, it's always a problem because if you break rotations like this.
Okay. So there is a little simplification in this story. It appears that instead of using this F, we can use instead of using full Jacobian here, we can use just some quite crude approximation of the Jacobian, which is just Jacobian projected to first S eigentensors. And the idea is that this F is essentially a version of R from which we removed all the relevant operators in a very vague sense. And yeah, here what we see in numerics. Here you see how F converges. Different lines correspond to different choices of S in this approximation. And we see that we can get to accuracy around 10 to the -9. And comparing this with shooting method would this accuracy for shooting method would require tuning critical temperature to 10 to the minus 23, which is below machine precision for the arithmetic we are using. So it's quite pleasant result. And what else is interesting that it's enough just to use projector of rank 3. So we barely change anything. We just remove epsilon, t's, and that's it. And everything converges. Okay, but does it help us really? Well, we still don't know if we can really prove that this critical tensor exists. But this Newton method, it gives us a handle, because now we can think that maybe we can take this F and analyze it somehow in infinite dimensional setting. Well, first problem would be to define, to have some RG map, which we will be able to extend to infinite dimensional setting, because numerical RG maps defined only finite dimensional tensors. And then we need to consider this F. And here is an example of what we could try to prove to show that there is a critical point. We would need to find the numerical critical tensor and to show that there is a ball around it, such that the Jacobian of F is bounded away from 1 by some constant rho inside this ball. And then if our numerical tensor is good enough, so if this equation holds, then we can use Banach fixed point theorem to show that there is actually a critical fixed point inside this ball. Yeah, this is it. I think I will not talk about disentangling because it's already 46 minutes. Thank you for your attention.
Thank you very much, Nikolay. So, there are any questions? We still have, I would say, 10 minutes for questions. So,
here you relied on the fact that your marginal operator had spin. That's why this rotation.
Yeah.
Let's say it's a scalar marginal operator.
Then we are doomed.
But I mean, in principle, the critical point will have a one parameter. It will be like one parameter count, right? So, is it really like a big problem?
Once you have one parameter family, you cannot use Newton method anymore because you cannot invert this operator. And so we don't have this nice handle to work with. Maybe it's possible to do something, but not this.
Well, there is like a flat direction in the direction of that operator, right? So, but in principle, anywhere along that line that you end up, it's a critical theory, right? You have like a line of critical.
Yes. Yes.
Yeah, but I guess you need to kind of leave this direction.
Yeah, we need somehow to get rid of it because otherwise it's just not clear how to prove rigorously that we have this.
So you mentioned there are some guesses about this tensor from CFT arguments. They are not Hilbert-Schmidt?
Yeah, they are not Hilbert-Schmidt, and they're defined using some regularizations. They cutting holes in the plane to avoid some singularities. And the beauty of this approach is that you don't need to do anything. You just take your Hilbert-Schmidt tensors and they work. And you can define neighborhoods, you can define anything. And this is what we would like to see.
But why do we want a critical tensor to be Hilbert-Schmidt?
Well, first of all, because you cannot even define contraction if it's not Hilbert-Schmidt tensor. If you have infinite dimensional tensor and you try to sum over one bond, you need this sum to be absolutely convergent. At least you want the sum to be absolutely convergent. And Hilbert-Schmidt condition is what gives it.
But could it be that the critical tensor is not Hilbert-Schmidt, but any neighborhood of it is Hilbert-Schmidt? This sounds bizarre, but
yeah, in principle, Well, no, wait a second. Hilbert-Schmidt tensors, I think it's a complete set, so it's impossible. Maybe I'm saying something stupid, but I think
Maybe
it's.
I'm saying something.
But I think that if you incite Hilbert-Schmidt tensors of finite Hilbert-Schmidt norm, it's impossible. But I'm really sad that I said this during the recording.
Presumably another way of forgetting some, maybe this has to do with the part you skipped, but forgetting some information is reducing the dimension of the index.
Yeah, this is exactly what is going on in disentangling. You need to define some effective notion of dimension.
Okay.
Because in infinite dimensional case you just have infinite. In numerics, what you're trying to do is just to reduce rank of your tensors, and this helps you to remove these TTL loops. Yeah.
So, sorry, you can do a similar procedure to this one, which you have sort of eliminated marginal operators using rotations. Also, if you have marginal operators charged under some global symmetries, right? You will define an arXiv map, which does the same thing, but also a rotation, not in say physical space.
Why not? Yes, I think it's possible.
So you can get rid of every marginal operator which is charged under some symmetry.
Yeah, I think it's. At least I will expect it.
Does this method apply also to theories other than Ising?
Yeah, indeed. You can. We are working with Ising because it's very simple, but what we did is we took RG transformations that already exist. It's called GIL. It was handled to us by Kliman.com, and we just added rotation and everything works. And this GIL itself, it's applicable to it.
In 2D.
Yeah, in 2D, yes.
What is guild?
Yeah, I said we don't have time to talk about disentangling. Guild is a particular way to do disentangling. It's graph independent vocal truncations.
So say you reach this fixed point and you have this tensor.
Yeah.
What can you compute with it and how?
You can compute CFT data using it, and it's a separate, very fascinating topic because you can in a network you can define dilatation operator, and you can really have a realization of your scaling operator in the network very explicitly. You just define the dilatation operator, you take its eigenvalues, and they are scaling operators. So you can do this. You can compute 3-point functions as well. I mean, fusion coefficients. Yeah, you can try to compute all the CFT data.
But it seems that you have more information. Because typically, like if I think of this in the Hamiltonian setting, right, when we compute CFT things in the continuum, we compute the dimensions, but here you have kind of the one-state wave function like that.
Mm-hmm.
So can you compute something more that we couldn't compute in the continuum? I understand that it's already interesting that you can compute the CFT data, but is there some more information this AC than that?
Yeah, I don't have answer for this right now, but it's a very interesting question.
What's more than reasons?
So for instance, if there are non-local operators in the theory, these should contain all of the information about their correlation functions. I'd say the O2 model, you have light, you have somehow this is very powerful once you get it. But it doesn't tell you just about local correlation functions. In principle, it's like the full wave function.
For example, you can compute the free energy, no?
Well, free energy, yeah, it's
That's an example.
also those things. Well, I know that you can compute some properties of some line operators. What you would consider to be beyond safety. Yeah.
Well, it's part of the extended
Yeah.
data, but not only about local operators.
Yeah.
And I guess you could compute also like the entanglement entropy or something like that, or some region.
Yeah, there is well. There is more than one way to define it in this setting, and you can compute. Yes.
Yeah, I mean that is UV sensitive. So even at the critical point, there will be some choice to be made, but there's a piece of it which is field dependent.
Yeah.
And this-
Yeah, I think you can do it. Yes.
From another point of view, and you at least it sounded to me like you were coming very close to the critical points. Can you use your tensor model near in the vicinity to estimate?
Yeah. This is what happens in numerics. We can compute CFT data just it's easy. Yeah.
So you can ask what you're asking. You can estimate else.
Yeah, numerically it's not a problem. We can do it for very high.
Come on, this is like very local information. That's the difference between this is like really you can build anything from this tensor. That's
Yeah, it's very local, but at the same time, it contains non-local information because it has this infinite dimensional space, and you can build anything.
I agree with that. That's what I mean. That's more than just information on a point,
Yeah.
because you can glue it in any way possible.
Yeah.
Okay, so are there any other questions? Very good. So thank you, Nikolay. It's very nice talk.